Okay, thank you to be here for the lecture of today. Just in a short introduction on working principle of mechanical actuators. And we will see, after introducing the working principle, the idea of the course, or this seminar, I would like to say, this hours together, is to present a model, a very important, we will see next semester within full course on dynamical systems, to present a model or dynamical model, which includes not only mechanical system, but also pneumatic system, hydraulic system. We will see the idea. The idea is to model an hydraulic and pneumatic system using, let me say, elasticity effect, spring effect. If you think about the possible actuator which use pressure, and the possible actuator that generate pressure with the fluid or with air. In any case, in both cases, we can see that we can use a spring model to represent or to describe or to predict. We will see in control if you will obtain the class in complementary study. This means I will present one frame in which with which we can model, let me say, not only mechanical system, but also hydraulic, pneumatic system. In some literature, in fact, we speak about mechanical actuator, including everything. Also, hydraulic, pneumatic, mechanical distance, because I would like to say also thanks also this possible idea to represent, which is a general idea. Let me really scroll down quickly because the first slides just probably think which you learned in different codes. To describe now in a mechanical actuator, we need equations of motions. Until now, we have seen, in particular last time, the model of an electrical system. I don't know if you remember the equations. The equations was three. One equation was basically the electrical equation, even though we have a component, is the reaction. You remember between the reaction between the mover, rotor or a linear mover, and the electrical part. Remember Lenz's law. And then we have the Newton equations, two equations, or one Newton equation, but anyway, in a mechanical system, let me say, we describe the motion. Somehow we know the meaning of these equations, equation of motion. It's something which came from the Newton law, which is important, the actuator, because the actuator moves, actuate, means this. Exactly. We can see in general two approaches. In this course, I have just time to show you basically the second approach, momentum force approach, Newton-Euler approach. Really, I would like to tell you something about the energy-based. I don't know if you know this, Lagrange. Not today, probably during the semester I sketch out just to know, I don't ask. Because what I do in the tutorial should be already done during the semester. The semester, I have just 4 lectures. But I will tell you, today, let me concentrate on the material of the exam, because we have the regular time. But basically, you have two approaches. One is energetically or energy-based. Lagrange. Do you know Lagrange? You don't know. You know. Oh, cool. Well, Benjamin Flusman. Yeah. Benjamin Flusman. I will give you just an idea, but not relevant for the exam, but in order to justify why we are speaking about, or we realize a model also using an energetical or energy-based approach. It's simple, believe me. It's simple. It's not so simple to understand some aspect of them, but But if I give you the equations, it's easy to represent. But of course, it's difficult conceptually. What we are doing in this course, I do it in this course, in this seminar, we will consider the second approach because first of all, you did a little bit. But anyway, it's more complex. How possible to say? But sometimes I would like to say physically is more interpretable because the concept of energy is quite abstract, if you see. But for me, it's not this the reason. Read, please, the last sentence. No? Allow real-time control. You know that I am control guy. My field is control systems. Of course, if this kind of model is more explicit in form, sometimes I use also energy base. It depends because really if the system is really complex, this energy based approach, if you don't care about where this Lagrangian come from, you apply the equation and you have the model in a very easy form. It could happen if you have a robot articulated with many arms, many legs, many joints. This energy base sometimes is easy to be applied. But for control, I would like to say it's more intuitive to apply the method which I presented today. But I am sure that is no, at least what I am presented here in 2 hours is extremely easy, believe me. But conceptually, nevertheless, also important. Also important. Oh, here's a little bit difficult. Now I try to explain, but now we will see the example is extremely easy because I will not consider everything which you can find in this really general complex state space equation. First of all, I didn't tell you what is the state space equation. Probably you can understand equal. No? We have an equal. Tau, torque, moment. In German is moment, or the torque. Yes. Yeah, a torque. What is torque in German? Un moment. Yes, one word. Okay, compact everything. Equals. Look here, is the quite general because you remember the Newton balance. I already told you when I introduced the movement of the rotor or the movement on the mover of the actuator, the mass. We can see here multiply the acceleration if theta is the rotation angular position of the rotor. Here it's a little bit complicated because theta is the vector, m is the matrix. Why that? Because in robotics, come to a new image, if you have many arms, many legs, this is complicated. And this matrix, this inertial matrix, depends also on the position of the mass. I don't know if it's not exactly the mass. It's the inertial matrix. I mean, in this position here, I have an inertia which is different. Here, we can understand. Here, I have to put more effort to stay in this position. This means this inertia depends on this angular position. Just intuitive. Here we will see the example which I do extremely easy because we will consider M, this element here, not in a matrix, but is in a scalar, which not depends of the vector of the vector of the angular position of the elements. I mean, I have here many angular. If you consider my body as a robot, I have many angular. This means you can think that this theta is not one angular as a sign, which I have to just to describe the rotational movement of the rotor. If the mechanical system is complex, you have a vector. And this inertial matrix should consider all elements in the robot. Excuse me, this mimic, but just to understand why I put it here, because it could be really complex. A little bit more easy is also this G matrix or gravitational matrix or terms, because you understand that the gravitational charge acting in this position on my is not the same if in this position. Here is 0, here is the maximum. This means depends also on the angular position with respect to let me say to the system which I consider the reference. V is a component that in the movement of an articulated system could be present, could be not present. I don't know if you know the Coriolis terms. Centrifugal, probably you didn't do many things about it. But let me consider that if it's moving, if I am moving, of course, we have also forces, if we are moving, disappear for in some particular condition. Coriolis, Coriolis force. It doesn't matter. If we are not here to learn this, this is really advanced robotics. But why I put it this? I put it this in order to show you how complex could be a representation of articulated system. Articulated, you understand articulated? In German, what is articulated? Artikuliert System.
So,
Many hands.
mit den Achsen meinen wir, ne?
Mehr Anzahl.
Ja.
And we can see that the dimension, m is n times n, v is in a vector, as g is in a vector, and so on. Theta is in a vector. We don't speak about this one. We will consider in a really extreme basic element in order to understand. And in the future, if you want to do something robotics, in particular dynamics of the robot, come to me in my lab, and we will can best understand this equation here with an articulated system. As long as I move in one direction, I don't need so complicated structure. Or with one rotor, we have just to represent the angular position of one element. The same if I'm moving the actuator, let me say linearly, geometrically linearly, I have to represent just its movement, left and right or up and down, no problem. We will do in the exam. The reason is that we have just this easy example, but nevertheless, the concept, except for Coriolis, also centrifugal force. Look at the system here. It could be that I need my manuscript. Look, you have two masses, just to introduce the topic. You have two masses moving in horizontal form, let me say in horizontal way, and we can see that the two masses are connected together with a damping factor, and they are connected to the external walls, let me say, using within the spring, characterized once by K1 spring parameter and Q2, K2, excuse me. D1 and T2, they are let me say, the damping between the mass, once with respect to the left wall and once with respect to the right wall, let me say. We have a force acting on one mass. To analyze this movement, we need two states, let me say, the state is more than two. We clarify what I intend for state is important because I use also this word without definition. I mean, I see a message now. Let me see. Because let me see the browser. What is it? I didn't. I don't understand. I forgot to share. Yeah, please stop me immediately because we already told a lot. Please tell me immediately because really here it's difficult for me to realize what I am doing. Sometimes I forget. Zoom has this problem. It's not Teams. We cannot share the screen. Zoom does not work. It's a shame. In Teams, we can share the screen. This means I don't have to care about yeah. Each time which I move for now, I don't have time to restart. Excuse me. I have to go ahead. But please, also it could be that I don't see the chat because I don't directly look at the slide. No, we are speaking here with the student. Please stop me because otherwise doesn't make sense. Clear. Excuse me for the error. But I mean, this inconvenient. The problem is that Zoom does not automatically, let me say, automatically share the screen. I have to change. I have to share. Let me say, each time which I switch between browser or anything. Excuse me. Yeah. I mean, to describe this mechanical system, we will say it's not exactly an actuator in this strictly speaking, but we will see that we need to understand a little bit the system here in order to apply these motion equations to an actuator. Because actuator moves. We will see to represent the system, the position of the mass x1 and the position of the mass x2. x1 and x2, I call the x1 and x2. About the state, we will see a little bit better in dynamical systems. About the state, I will tell you in next semester in the course of dynamical systems. But I would like, nevertheless, to anticipate the concept. The states are variable which reflect or which represent the energy of the system. I already told you, nevertheless, a little bit. Do you remember? Current and current represent the energy in the coil last time. Position represent the work. Do you remember this? And the velocity represent the work is energy. No? Joule, work is energy. The velocity represents or reflects the kinetic energy. I told you a little bit. Here we have 4 states. Why that? Because we have the work of the mass m1 because it's moving. We have not only the work, we have also the potential energy, which you can see in spring. And also the kinetic energy because it's moving. I assume that I move. No? You have an effort. For both. This means 4 states. But about the state, I told you also last time. How I can describe, how I can model the system here. Model means to attain x1 and x2, for instance, as a function of everything which you see here. Let me be a little bit more concrete, based, of course, on the Newton principle, because we have an effort, we have a movement which can be described by Newton equations. This is written here. Now we have a different way. Probably you have seen this. I don't have to spend a lot of time. With Benjamin, we have seen more complications. Yeah, this means I don't want to spend a lot of energy, but look. Which kind of forces we have in the system here? We have an input force, F of t, which came from outside. Could be, another pneumatic system, could be an electrical actuator with the mover, exactly what I told you last time, which push. For instance, push or the pull, the mass m1. Then very important, we can see here that we have the stiffness force. This I would like to consider in this sense, and spring force, inertial force. We can see what I intend. M multiply the second derivative of x in general. Now x in this case is x1. K multiply is the spring. And then we have this stiffness effect or stiffness force. Because we have a friction, a friction, we have a spring, we have this friction which we can see expressed here. They works, please pay attention, we can see here, this here in this balance here. In this balance here, in accordance with the Newton balance, the mass multiply the acceleration, you remember, equal the sum of the forces acting on the mass. This is the Newton principle. No? In high school, we learned mass multiplied acceleration equal the sum of the forces. Benjamin told you probably something more. Let me go ahead quickly. We can see that in this kind of system, we have not only basically the spring force or the stiffness here in general FD, here FD1, because we have two elements if you look at this equation here, this scheme here, excuse me. But we have also the force acting against the mass, which is basically the reaction. The reaction, very important about the reaction, I told you a lot. When we have an action, we have always a reaction. We have seen also this important reaction of the mechanical system on the electrical one. Please, this is also in the principle, no? It's the same principle. F equal m multiply A, or the sum of F. Formalized mathematically, yeah, physically, mathematically, what? When we have an action, having a reaction. I don't know if you remember this. I mean, here the action is S of t, all the rest is the reaction. Inertial reaction, m multiply x dot dot dot, and the sum of the forces which works again, because the nature of the system doesn't work, that don't want to move. I mean, you remember this concept of the nature is lazy. We can see also here. If I try to push, to pop, to pull, in any case, you have the reaction against this action. You remember also this back effect in electrical system. Quite here, you know the context, but it's the same. We can understand that the spring works against this damping element of the friction works against, but also this one. Why that? Because if you fix M2, it's clear that works against. Just to express. Then we will see if this is moving, how change, but always against. And not only, also the inertia works against. I mean, big mass is more difficult to play. It's to move, or to be moved. Yeah, this means no wonder this minus here. No? What about D12? Yeah, we will see later, which is equal the reaction of the mass 2 on the mass 1. But for the mass 2, for the movement of the mass 2, we can do the same consideration. I don't want to repeat, but probably you know better than in this course by Benjamin. But anyway, the second part of the system here can be analyzed in the same way. In any case, also here, everything works against everything in this case, because we don't have here active force on the mass 2, because the force, or the active force, is active on the mass 1. This means the mass 2 will move, let me say, because of a reaction. No, we will see what I intend. The reaction is this, anyway, this is a particular reaction, the reaction in between. Everything is in a reaction, because these elements here are a passive element. Something which try to be against the movement. But in one sense, we can write in this form here, and this form here is equivalent to this one. Now, when I can use this one, when I can use this one, it depends which balance I am considering. Let me express here what I intend. Look, in the first equation, I have a plus. In the second equation, I have a minus. Why that? We can express this looking at these two terms, but basically, I can write these two terms both in symmetric form with minus. I mean, here it seems to be quite natural, it is a minus. Here it's a little bit strange, but look, here we have x2 derivative minus x1 derivative. This is the meaning. In order to clarify plus and minus, my idea is, or at least a possible interpretation, we have many possible interpretations. And looks again at this picture here. As I told you before, if you imagine that M2 is fixed to move, this means D12 is something which works totally against, let me use totally against the movement of mass 1. This means minus 1, 2, which multiply x1 derivative. Again, this friction effect is against the velocity because it's against the movement. The velocity stays the movement. Yeah? Velocity can associate with the velocity of the movement. What characterizes the movement is the velocity, not the position. Clear, no? How conceptually. Now, if you agree that's against the movement one, we have an effect of friction effect minus d12 multiply the velocity. Better to say x1 derivative. Of course, the reaction will be less if M2 move. This means if M2 move, we have D12, which multiply x2, but with one minus. I mean, the relative velocity, now to conclude, between M1 and M2 is x1 minus x2. I don't know if this is clear. This means in this equation here, I can really justify minus here x1, excuse me, the relative velocity x1 derivative minus x2 derivative. I forgot to say derivative. I can say here minus d12, which multiply x1 derivative minus x2 derivative, which is the relative velocity of what? Of the mass m1 with respect to the mass f2. But here is the same concept. When I write the dynamics expression of the movement of the masses of 2, we have a reaction, negative reaction, always against the movement with respect to the relative velocity. This is the relative velocity. You understand the relative velocity? X1 derivative minus 2 derivative is the relative velocity, relative means between the velocity m mass 1 and the velocity mass 2. I don't know if from home you can see me. Assuming that you have here a damping factor. If my left hand and my right hand, they have the same velocity, I don't have a stiffness effect. Like I'm a little bit single. If this is moving slower, this will act on the left hand with an effort because of this stiffness aspect. Or probably it's better to see on a surface this friction effect, but of course you cannot see exactly what I'm doing. But always against. Why that? Because we have a passive element. Against the movement, against the velocity. Okay, I hope no mistakes in this calculation. Typically in control, therefore I told you in control very often is used this kind of balance. Again, it's difficult to build this. From Benjamin, by Benjamin, you have seen a complicated situation, or whatever.
Yeah.
But here you can see that probably Benjamin represented the system in a different form. Here we will see now in control form. Why that? Because at the end, an actuator must be controlled. The goal is to be controlled, otherwise, what are they going to do? Now we divide both by the mass. For the first equation, we divide by m1. For the second equation, we divide by m2, and we have this expression, this expression. And look, nevertheless, we add also, we can see here the derivative of x1, this is v1, the derivative of x2, which is v2. But this is just to kinematic expression in order to put explicitly the velocity, not only in control, as I told you last time. We need very often, let's see here, the equations in form of matrix expression, in which basically I don't remember last time I told you that this expression here, which basically is already here, I reorganized in dynamical form, in which we have here x1 derivative equal v1. At the beginning was here. Typically, we order in this form here. And x2, x1 dot, the second derivative, x1, is basically v1 dot, no? Because of this. You can put here v1 dot. And you can do the same here and here. Why this form here? Why this form? This form here is useful because, as I told you, position and velocity represent the state of the system. This means represent the energy of the system. And what is important in control or in general to describe a system, to put in evidence, to put explicit when and how, better to say, the energy changes. This means for us it's enough to write everything in an explicit form of what? Of the derivative of the position, which is the first state in this representation, and the derivative of the velocity. Because we have inertial, work, and we have a spring, which is represented by the variable position. This means the derivation or the variation of the position is important for us. In our case, it's just the derivative of the position is the velocity. And here in this equation here, we have the derivative of the velocity, which is this complex expression for the first mass and for the second one. I can show you, but I already told you last time, how this expression here is equivalent to this one. A little bit more comfortable if you work with software and so on. But if you remember, I told you last time, no, rho multiply colon, if you do everywhere rho multiply colon, I will obtain these equations here. This is more mathematical, more physical here. These tables can be used very in an efficient way in the computer. Here's the same. Here is a similar situation in which we can know a little bit more concretely see in a possible system which is somehow concluded that this is no, it's not this suspension. Here a little bit visible. We have a wheel with mass m1. We have the chassis with the mass m2. We can see here probably this is better. I don't know if this is better. It is better probably this picture here. Believe me, this is a really complex system. If you include also some non-linearities in our course, I don't consider non-linearity in order to show you what I intended. Here a little bit the model a little bit different. Here I would like to say a little bit more realistic, because this element here characterized by K1 and dr, Kr and dr, this represent the characteristics of the pneumatic aspect. Now we can understand already from this picture here how in a pneumatic behavior, in a pneumatic component, can be represented by this spring and damping factors. Look, if you think about here the wheel, Here the wheel is not there. Anyway, let's try to imagine. Of course, the wheel is characterized by a mass, number one, and also by the pneumatic aspect. Of course, here is quite abstract because I don't see the wheel, at least here. But I try to localize the mass in one point, and I try to localize also this characteristic, physical characteristic of the pneumatic between 2 points. Which one? The mass point and the ground. Yeah, this kind of model here, we say this is a model with concentrated parameters. Concentrated parameter means that I fix the mass in one point without dimension. One point doesn't have dimension. One point is characterized by, well, this is a point is a little bit complicated to define, but is a circle without dimension. We collapse. It's in a disk. Oh, circle is also possible. It collapse if you don't have the radius of this disk is going to zero. We collapse in point. In math, we have a more precise definition, but it's intuitive to understand. This means it's as if this mass of the wheel is here at this point, and between this point and the ground, we characterize between these 2 points the pneumatic. But now we can understand that pneumatic, hydraulic, we can nevertheless represent everything using these 2 parameters. Now, between M1 and M2, we have a similar situation. Here is a little bit difficult to see, but here, yeah. Assuming that here we have the axis of the car, we can see here, extremely complicated, but an axis. The axis is fixed on the wheel. Consider just a quarter of car. Because if you consider an axis complicated, extremely. If you consider everything, 2 axes, it's extremely PhD problem. Here it's basically the same as Dirk. I stop.
Ich will dich stören, ich wollte nur guten Tag sagen. Ne?
Danke, sehr nett von dir. Ciao. Let me analyze directly this because it seems to be a little bit more real because we have here this damping factor is there in the pneuma. It's more damping than the elasticity, I would like to say. I'm not expert in this, but let me analyze this. But it's not far away with respect to what we did before. I mean, we have 2 masses as before. This means this balance here represent the dynamics of this mass here. Let me see if I made mistakes. No, it's yeah, I see mistakes. Please pay attention. Dot. Dot. Please correct. Dot. Let me see if I have other mistakes. I hope no. It could be, but do you remember I told you at the beginning, I have a better presentation. I told you it could be that because I have a LaTeX, this presentation I have a LaTeX, but I didn't find quickly. I have a LaTeX, but it's just it's intuitive. That's something which remains in the representation. I try to find a better representation. Dot. This we have seen also before, but in terms of velocity, we can see this. This is exactly as I explained before. Here, why now we have in terms also of spring effect? Because you have this KF here. Excuse me, here is capitalized, it's not capitalized. As I told you, we have a better lecture somewhere. I have a better lecture somewhere. Excuse me for this error here, x2 ... I upload in my study the better lecture. KF is capitalized, also before anyway, it's the same like here. But you can see that this relative velocity, which now is responsible for the reaction, is also, the concept also here, because here we have the relative position, which is responsible for the reaction between. Before we didn't have this, because in this system here, we don't have in between in the spring. I don't know if this is clear. But Benjamin, I would like to go a little bit faster. I can do the same here, but we can see that I change the sign. I change the sign because it's opposite the reaction. I told you before, quickly, but I told you before. Now, the dynamics of X1 a little bit more complex because M1 is related to the movement or to the dynamics of M2, but is related to the ground. Therefore, we can see here that I have to add these two terms in which X1 of the ground is 0 because we consider this element as a reference. When I fix this element of a reference, the ground is the ground, does not move. This means X1 of the ground, or the X of the ground derivative is 0. This means I have to add these two elements which reflects, let me say, the reaction between, or better to say, the movement of mass M1 with respect to the ground. Very important. We stop in 5 minutes, we go to Mensa, no? As always. Very important now to consider, I mean, in the exam, a possible question could be something like that. I will show you a possible example. But more probably, I will introduce very often, and then I will do with the manuscript, such kind of systems, which basically are very important in, let me say, electromechanical or compound actuator, because this kind of system, which you can see here, allows to compound, to consider an electrical part, which is piezo, for instance, here. It could be also F1 generated by an electrical mover, an electrical actuator, as we have seen last time. But this element here, which allows to adapt force position from left to right, force position from electrical actuator, piezo, for instance, or linear motor, and this part here, mechanical part, is extremely important because very often with the electrical system, we are not able to obtain, let me say, very fast movement or large enough displacements. But we have a big force. It's the case of piezo, but also the case of electrical actuator. It depends. Now, look at this. I will not do in the exam this system here, in which the fluid inside could be air, could be oil, is considered compressible. And the compression, or the effect of the compression, can be modeled with spring very often together with the damping factor. Yes, I put just the spring, but think about also damping factor. The mass here of the oil is concentrated in one point, because if it's not concentrated, the model is more complex. You remember, I told you this kind of model, the name is model with concentrated parameters. This means I concentrate the mass of the oil of an arm of the rope in one point. I don't know if Benjamin told you about this not concentrated model in which we are analyzing this partial differential equation. So, this is the program typically, or PhD program and so on. Also last time we worked with concentrated parameters in one point without dimension. Of course, here the mass cannot be concentrated here because the mass is distributed. This means in some edge, the pressure is different. I mean, it's a very abstract system. Let me stop here. We go to Mensa, and then we will analyze this kind of system here and using my manuscript. in order to converge at the end on a very easy balance, which allows, with the manuscript, to propose an exam exercise. An exam exercise, I would like to say. At the end, I will conclude with this system here. And yeah, here we have a more complex system. I will show you this, but just because we have a project in my lab. We have two Segway, you know, the Segway. Based on the system here, we can analyze also the Segway. We have this in the lab, two Segway, you know, the Segway, the politics. Running with the Segway. Yes, a little bit inverse, but if you put this element in the upper part, Segway is lower than Segway. The analysis of this dynamics with the Segway, with respect to the Segway, is the same. But this is not the program of the exam. Also, this one, I don't know if I can ask build the dynamical system of the simple pendulum, but this analysis, yes. I will concentrate on this analysis here, and I will concentrate on the analysis of the gear, because in mechanical system, we can find this kind of element as an interconnection between the electrical and the mechanical part using a mechanical system, but we have here fluid inside. Could be oil, could be also air. Never test fluid. Of course, air is a little bit strange to call fluid, but in our model, they are characterized by different spring effect and damping effect. Here, the damping is not considered, but think about that, must be there. Very often, not very often, typically the damping effect is stronger than the spring. We didn't do this analytically, we don't have time in one block. We will consider not compressible fluid. This means here is connected directly. Directly means rigid, without compression. But think about, with this kind of model, we have seen also here. Here, better. The pneumatic is represented by the combination of the spring, let me say, and friction effect. Allow me to say so. Exactly so. Inside, I think we have the spring, and the friction is exactly the friction between the spring itself, the real spring, at an friction in its material. Losses. In fact, if you compress the spring, you realize that you lose energy in war. We transform. Lose is not correct. We transform energy. We realize that the temperature of the spring is increasing. Probably you did this. Yeah. Okay, we go to the Mensa. We will come back maximum half hour, and the rest of the lecture I will do an exam exercise based with the manuscript on what is doing now? On this example, and then on the gear, this is also on a gear somehow. But of course, hydraulic gear, mechanical gear, pneumatic, as you want. You can call it as you want, because we will see in the exam, I will consider rigid. But of course, if you consider a model which includes also here inside spring effect and damping effect, is extremely complicated. Even though it's still, at least in this representation, we want to do, or we can do in both model concentrated parameter, it's not so extremely difficult, but if you do in the distributed parameter, really this is a PhD program. Okay, I try to stop here. We take half hour for lunch, and then we will come back. See you later. Okay, let me restart. Reconsidering the last slide, or one of the last slides, which we considered before. Again, we can see here in a nice picture in which we can see a motor, basically. The actuator is a little bit complex because, of course, it seems to be, it is, an horizontal movement must be converted in a vertical one because the valves, intake valves, in German is Auslass, in English is, I don't remember the name because basically you have to say, we implemented this actuator just for intake exhaust valve, I think. Intake valve and exhaust valve, yeah. We implemented just for the intake. The reason is the exhaust valve is more difficult to be controlled because in the opening phase, we have to work against the pressure inside the cylinder. This is extremely difficult to guarantee that the valve, exhaust valve, does not crash against the cylinder. I don't know if you can figure out. Last time I told you a little bit about that. The project was basically finalized to replace just the intake valve from the cam, the same cam, Knock and Valley. Now, in this particular case, I would like to speak about this. We have a piezo system. Andreas told you about the piezo, probably a little bit. We will see that in our case, we don't have time to go in depth on the piezo, but in our structure, the piezo basically generate force in our extremely rough model, generate the force without dynamics directly with a factor between, we have a factor, let me say, between voltage and force. Basically, I put, I don't know, 15 volts, 12 volts, I generate a force of 1,000 Newton. This means we have a factor of 1,200. This means we have a factor of 100, which multiply the voltage. Of course, this factor is a physical factor because we transform voltage into force. But of course, the piezo system in an extreme complex system, extremely. Andreas told you a little bit. We had a PhD program inside this control just on the piezo. And then, of course, another PhD program, the focus was not the piezo, but the motor technique. Also, to synchronize intake and exhaust. Exhaust was connected with the cam, and the intake was free. The idea was to mix fresh air with combusted air, but just controlling one valve, intake valve. In German, I think it's Einlass, no? Einlassventil. Yeah, look, in this particular case, but can be used also in the linear motor. Linear motor is exactly what I told you, this voice coil, instead of this. Could be probably enough. No? Why we didn't do for different reasons, but now I would like to focalize to the exercise for the examination. Again, if you have here oil, as in this case here, we can consider a model of this system here. We need this system here. Why that? We need because in particular case for the piezo, but also for any actuator we generate, but the piezo is particular. Let me remain on the piezo. We generate a very strong force. The piezo is able really to generate strong for 1,000 Newton or no problem. It depends on the length of the stacks. It's characterized by many particles, many cells. But the piezo has the problem that generate a very, let me say, short displacement, and also not so large velocity, I would like to say. This means this system here is able to transform, let me say, the word is transform, it's a transformator in electrical system. Large or the big or the strong forces from the left part to small forces, but enough to the right part, but increasing the displacement. Yeah, can be done with this system here. Now we will see how it's working. And the model of this ratio, this ratio or gear is not exactly a gear in the specific term, can be realized with hypothesis of compressibility. The hypothesis of compressibility is more general. This means we can model here with a spring and damping, not only with a spring. I don't know why the student didn't put also the damping factor. But could be done, as in our case here in the lecture, considering not compressible, compressible fluid here inside. Here is a spring, a real spring, a physical spring. Here is this spring here is a modeling spring. We don't have inside the spring. But if you think at the possible compressibility, do you remember when I told you about the pneumatic? We model this compressibility of the pneumatic using spring and damping factor, or the spring factor and damping factor. This spring here is the physical spring because you know that the piezo can work just in one direction. It's pushing to come back. We need a force which can be realized by the spring. This means the force that we have here move on the right, basically charge, let me say, the spring with energy, and then the spring in the phase back, let me say, act to bring the piezo in the start position. Anyway, here is not explained how this vertical movement is transforming. Excuse me, that's this horizontal movement is transforming into vertical one. There is an hydraulic system. Just this idea. Here is not comprehensible because I am moving horizontal and I have to generate in the vertical movement. We have a complex hydraulic system in between. I don't know if I have here the picture. I will bring you in the tutorial. Look now about the system, then we will go in depth with the manuscript. And then we upload, believe me, everything. Yeah, again, in this course here, we assume that the oil, or whatever we want inside, results to be incompressible. Now we will see what is the meaning because we discussed before with you. But the incompressibility is stated basically by this easy equation. The translation of this, the explanation of this equation here is basically in this this sentence here. Basically, F1 divided, you can read in this form here, F1 over time, F1 change over time, because the piezo here is not indicating, is controlled, depending of the cycle of the motor. It's a very big project, we can understand. It must be synchronized with some signals. F1, you can read this, F1 of t divided A1 equals F2 divide F2 of t divided A2. It's written here. Is everywhere the same. In all points, in the edge, of course, it's not the same, but let me assume this. Of course, is this hypothesis not guarantees? This means the system is compressible. We need to obtain this force here, also here, time. This means we have a distribution on the displacement of the signal impression. Is this case? If you consider compressible also with, not only with spring, but also with the damping factor, we can understand that the signal impression, the pressure signal from here to here, need time in this sense. Or better to say, you can say also time, it's not wrong. We have a phase delay. I don't know if you understand what I intend. Try to imagine a sinus, because if you have here damping, we have an damped, could be an oscillation in terms of pressure, a damped oscillation here. But I mean, let me consider a practical example. I give a force and a constant force here. Before having a constant force here, even though reduced, I need time because we have a wave because of these dynamics inside. If the physical, let me say the fluid is uncompressible, it's connected, let me say, rigidly with a rigid element here. This means exactly say that the pressure on the surface A1, let me see here, equal the pressure on the surface F2. Here we can see very well because the pressure is the force divided the surface. If it's compressible, and you put constant force for it just to understand, we have this, but after the transient, when the wave is passing through this displacement. Let me show in a figure out way to show you this. We say sometimes quasi-static configuration. I would like to say static configuration, huh? But in the book they write quasi, but static configuration. Now look, this equation here can be written in this form. Why that? Because the surface A1, let me see, I don't see well. This equation says, if you consider here the picture is not nice. It's not nice. But if you consider the volume which I move of the fluid inside here, this means the volume which I move is not compressible at each time. Like this is valid at each time. It's the same, left and right. Yeah, the picture is not so nice to understand this, but try to imagine the volume which I move on the left. I will put another better lecture. The volume which I move on the left, if it's not compressible, is equal to the volume of fluid which I move on the right. You have this experience probably. We did the hydraulic system in the sense, but you can imagine if I move here and the mass of the liquid, why not? If it's not compressible, this means also the volume moved on the left equal to the volume of the right. Now, if I divide this volume, which is equal, with the corresponding linear, let me say, linear movement, x1 and x2, of course, I can cancel here, the volume. Again, A1 is equal the volume which I'm moving divided the linear moving part. I don't know if this is visible. X1 is different with you because we have a different A1 and A2. Again, the A1 is in a surface orthogonal to the blackboard. I don't know if it's orthogonal to the blackboard. A1 is different with A2. If the fluid is incompressible, the volume which I move is the same. I have another presentation with a better picture. Divided the two different displacement. Why different? Because we have two different surfaces, but the same volume. I can write this expression here in this form. Nice. Now, exam question. And then we go in depth with a more complex exam question. Try to describe, to model this system here, probably having a better picture. I don't have, in a better presentation, I have a better picture, which we have here in the wall, because here it seems to be a little bit strange. Having a better presentation, which we have here the wall, because we have here the wall, yeah. It's fixed, this movement somewhere. Yeah. Of the, let me say, moving mass on the left part, we can see here, of the moving mass of the left part. I show you what I intend. M multiply x1 dot dot, M is the moving mass, equal F1, this force which is given by the actuator, it doesn't matter which kind of actuator, which came from the electrical system, minus this friction part, what I am losing, assuming that I know KV, but can be identified with complex algorithm, minus F2. What is F2? Yeah, here it's this force here, which works again the movement, let me say, left to right. Which in our case is given by, if I don't consider other components, let me say the antagonist spring, for instance, Kf multiply x2, because do you remember that the spring is acting proportionally with respect to the position. This means I plug in this here, and I have this expression here. But in order to here we have a wall. No? I have a better representation. Here it's fixed. This point is fixed. Please imagine this point is fixed. Yeah, in a few minutes I give you a better. Now, to represent here in this easy example the dynamics of the first mass, it is enough to plug in x2, but we have x2. You remember? From the initial considerations, I told you that f1 divided f2 is equal x2 divided x1. You remember this? From this to this, I didn't explain that deeply by this, because x1 and x2 both are in the denominator. This means v and vi cancel. I didn't explain, but it's easy to see. No? This means x2, considering this, is this one as a function x1 and parameter, yeah, a1, a2, which is a given, or please pay attention, can be in the constructing phase when we design the actuator, could be considered exactly with this equation. What is the force which I have to obtain on the right path, which should be enough to reach our goal? And in the meantime, how long I have to move? This means in the design analysis of this ratio translator, as you know, as you want. We can design the surface meter square or centimeter square. But now in our goal, if the question is, because we are here to learn, and we will go in depth the next semester in dynamical system, we are here to learn to model the differential equation. Just let me say an introduction. Next semester we will see more in depth, really, because I have a full course. I am alone. Yeah? And this we can do exactly the program which I want. But nevertheless, I think it's good if you in this course, in initial course, you see some model structure, or to see just roughly how a differential equation can explain the movement of my actuator. Look, now everything is in the function x1. When I say please describe the dynamics of x1, I intend that in the equation should appear parameters, of course, but just the variable x1. Probably you remember in Math 1, no? The solution of differential equations, or the Math 2. Yeah. This means if I give you now the initial conditions, you remember 0, 0, for instance, I give you a force. Why I say I give you? Because the force is given by the controller through the piezo, for instance. And you can find how change over time x1, x1 derivative, and x1 dot dot, second derivative. This means we can characterize, we can analyze the performance, I would like to say, in terms of velocity, acceleration, particular velocity, and position should be enough in accordance. Now, it's a little bit too difficult to understand because what is the meaning enough displacement? Yeah, inside we have an hydraulic system that give power to the valve in order to close and open intake in our case. And this piezo moves, basically activate one channel, another channel of hydraulic system in order to open and close the valve. If I find quickly, probably next week, the picture I will show you a little bit. Also now at the end, go ahead with the exam exercise. And you can monitor or you can simulate position, velocity, but also the acceleration is important in order to evaluate if we have enough force. I mean, now we are not here to analyze the design of the actuator, but you can understand that to analyze the dynamic of the actuator, this means analyzing means after that to design a good actuator, we need exactly position, velocity, acceleration in order to see then multiply by the mass, the force which we have at disposition in this sense. Okay, this could be an easy question to the exam. Of course, I don't ask the solution of differential equation because this is a math exam. You already did. For us, it's enough. This, of course, in my lab, if you want to analyze or to go in depth, not necessarily in the actuators, very often we use, almost always, we use the MATLAB Simulink in order to find numerically the solution, even though in this case, the solution can be found also analytically because it's in a linear system, second order. This means no problem to find the solution. Also manually, but here in schools, we don't do. In dynamical system, we will see that I will introduce also the solution of the differential equations, even though you already did in math, but we will see different aspects of the differential equation. We learned again to solve the solution in a different form. And then a little bit I will tell you about the MATLAB Simuli, even though the MATLAB Simuli is in my complementary courses. Of course, in bachelor thesis, you can do with me. Now, let me go in depth on this. And at the end, I will conclude with an exercise. It's a little bit, I don't want to say more difficult, but let me see what I have here. That is not more difficult. It's the same. No, it's let me see. I am looking for here. I see an error here. Oh, excuse me. As I told you, no, let me just a second. I'm looking for another exercise. It's okay, I think so. Okay, I would like to propose this example here now. Mhm. Um, I'm thinking 1 second. X2. Yeah, I see an error now. Oh, because I told you this is not exactly what I intended as a representation. Let me show you the right solution directly now, and then we will go a little bit more in depth. Yeah, excuse me, but do you remember I told you this is not not exactly the presentation which I want to. Okay, let me do the solution. Excuse me, the right solution, but it's not much, no? And then we will go a little bit in depth. Okay. We will find something. Yeah, there is an error also there. Okay, let me. I don't have a better way to do it the same. What did you see? Ah, here. Yeah, 1 second. Look, exactly the same exercise, a little bit more precise with the wall, because we have inside the athlete of this wall. Um, about that, you remember I told you? I told you because this is if x1 is the displacement, is the volume which I'm moving on the left, it is the volume which I'm moving on the right. You remember, this I already explained. This also I already explained because this means F1 divided F2 equal A1 divided A2. This means the pressure on the surface A1 equal the pressure on the surface A2. Now I show you the error which I did. From here, this expression can be written also in this form, right? This expression, let me, excuse me for the error, but remember I told you this is not the right presentation. This expression here can be written also in this form. Now look, the force which we have let me say, acting on the left part, basically, like this is the error. Basically, on this surface, on the surface A1, surface S1 is orthogonal to the blackboard. If you look at the blackboard, of course. F1, or orthogonal to the table, my table. F1 minus, do you remember? Uh, mm, Let me say why this this is the correct one. Ks, just considering this friction part, which is multiplied what? I have to consider everything which is acting on this surface. This was the error which I mean, reading the slide, I didn't realize the beginning there was an error at this point because I am considering x1. x1 is characterized on this point. But on this point, x1 is this. Yeah, let me see. Is let me see why. Um, there is also here an error. Let me see. Okay, okay. This element here multiply x2 ks is the force F2. How I can express this? We can see from here. Because ks, which is this spring here, is multiplied by a displacement, which is, let me say, amplified by A1 divided A2. Now, oh, I made mistakes. I think it's okay. Let me look at this. This is relatively easy because I have just to transform F2, which is this one, on the point 2, which is basically here. It means here, no doubts. This is enough to transform the force. Here, you have Ks. I have to transform the force on this point. This means this is the reaction, yeah, because on this surface, let me say we amplify the movement. No? We amplify the movement because A1 is larger than A2. Do you remember? We reduce the force, but we amplify the movement. And this point here. But I have to transform x2 in x1, this one. Therefore, I have this square. I remember that in the slide was wrong, that this is correct. I try to express again. The movement here, which is responsible for the reaction force, is basically something which is larger than this one. This means is x2, which multiply this ratio here. Again, if x2 must be transforming into x1, we have exactly these two equations. First equation and second equation. In fact, in the piezo, we have to really be careful on the reaction, which is very strong, which is very strong. This is square. Let me now shortly, the rest is basically, I already told you, is the repetition. That is very important, this part here. Let me now conclude just with some general considerations. Again, general consideration. Everything is known. This is something which we have seen in a different form. Do you remember we have seen that f1 divided f2 equal x2 divided x1? We have seen in different form. But what is the meaning of this equation? This is the work. Force multiply the position of this part equals force multiply the position on this part. It's the work. The work on left equal the work on right. As you remember, I told you in terms of incomprehensible hypothesis, the volume, no? This is exactly what I am telling you now. No? The volume on the left equal the volume on the right. But of course, fluid is not compressible. This equation holds always. This holds in case the fluid is not compressible. From here, we obtain this. No? And again, it's not compressible. This we have seen also before. Now look. I can write in the meantime that the mechanical power on the left is equal to the mechanical power on the right. This means from here, I can write in this form. This means this equation came directly from here. Why that? Because f1 divided f2 is equal a1 divided a2. Because of where it is here. You have seen also before. Conclusion. x2 from here is equal to x1 multiply a1 divided 2, and x2 derivative is equal to a1 divided 2 multiply x1 from the power balance from here. But could be also obtained if I do the derivative of this, because here we have basically a kinematic relation, no? Between or the relationship between position and velocity. Question: what about the acceleration? This is the problem. The acceleration is a dynamical variable, it's not a kinematical one. This means I have to consider the balance, the dynamical balance. In this sense, we have also this ratio. Let me show you what I intend. we have this expression here, which it seems to be a little bit a contradiction with respect to this. But where this come from? Come from this equation here, which we say that the force multiply the velocity, based as I told you before here. The force multiplied the velocity is dot on the left equal the force multiplied the velocity on the right. If I write everything in this form, and if I assume that we have the same fluid, this is normal, I can have the same mass. This means I can at least in this kind of actuator, we have just one fluid. I can write this from here, I can cancel. I will obtain exactly this equation here, which is basically this. This is the natural form. Again, the volume is the same, with the same fluid, the density is the same, is the same mass. We can see that if you now consider x1 derivative divided x2 derivative from here, which came from the same, I will obtain exactly this. Let me see if I can say something more about this. Yeah. To conclude, to confirm a little bit this expression here with something which we know probably better, because it's more intuitive, the gear, which is the equivalent which we have seen now, but let me say in more mechanical, in a context which is more mechanical. The other one is, yeah, it's mechanical, but in the sense of fluid. Look, we have, let me say, a wheel characterized by radius r capitalized and a wheel characterized by a radius r not capitalized. Wheel number one, wheel number two. The wheel number one rotates with the omega 1 in this direction, clockwise. Wheel 2 rotates anti-clockwise with omega 2 in this direction. This means torque on the first wheel multiply omega I1 equals torque on the second wheel multiply omega 2. Exactly this, the power. Assuming that we don't lose power in the connection. Now I remember probably why the model in the slide of this ratio is the spring. The reason is we didn't consider losses inside, but anyway. C1 is F1 multiply R. It's basically the force which can apply and multiply the radius. No, this is the torque. C2 is F2 multiply the radius, but considering the wheel number tau. This means I can write everything left and right in this form. If you remember that just to remember this R multiply omega 1 R capital I equals R not capitalized multiply omega 2. The name is this tangential. It's the tangential velocity. It's the tangential velocity in this sense. This means from this expression here, assuming that we don't have slip from here to here is clear. It's similar before. This is similar before, if you remember. Quite similar. Large surface, small surface, large radius, small radius. Again, as before, what about the omega dot, the angular acceleration? Omega dot is the angular acceleration. Yeah. If you consider that the power 1 is equal to power 2, you can also see in the other direction. The other direction. This means j omega 1 derivative multiply omega is the power on the wheel number 1, and this is the power on the wheel number 2. Do you remember we did it similar before? M multiply the acceleration, multiply the velocity. Here, everything is in the rotational form. The mass becomes J. Of course, in the ideal form, as I told you, which we don't have losses. Otherwise, of course, we have to consider that the energy or the power which you have here is not totally transferred here, but let me remain here. It's a little bit more complicated, just to understand conceptually. And now, from here, we have a similar expression as before. A little bit, let me say, more complicated, because now we have to wait by I1 and I2. But of course, if the inertia is the same, this means in this case means different material, of course. We can obtain a similar expression as before, which we can see is inverse with respect to the expression of the velocity. Exactly that we have seen in fluid, which we have the inversion of the surface. Of course, if J1 is not equal J2, yeah, because J1 equal J2 means, you remember, in a disk, this is the inertia J1, this is inertia J2. Let me see how I can tell you a little bit more about that. Why doesn't work? Probably again, that the acceleration on the second part is A divided 1 multiplied the acceleration of the first part. Doesn't work because we have a different dynamics between left and right. This is the concept. Let me see what I can add here a little bit. Let me see. Mm. Okay, I don't have a I think it's okay. Uh, okay, if I forgot something during next week during the tutorial, I can improve a little bit also what I told you until now, but I think this is a little bit of a repetition. Yeah, nevertheless, you know that, no, already, but just to build an analogy, no? Just to build an analogy. Very important, these two expressions, but at the end also this one. That we can see. Okay, I think today we can conclude here. Next week, the same time, I think just per Zoom. If I will be here, nevertheless, I will, in both cases, I will inform exactly in which format we will do the lecture. And next week, we will try to go through these three possible questions. I don't know how many I will put, basically, the basic concept of the actuator, using this example of the coil which is going inside the magnetic field, and then the differential equations, three differential equations of a model in which we have L and M, basically consider the transient, block diagram or something like that. And then connected with this to graph, do you remember the curve of the output? This connected with this, basically, I give you the differential equation, the questions are block diagram, and then eventually to graph, I don't know, velocity, current, something like that. No? And this year, about this year, I will insist a little bit also next week because yeah, it was now the last yeah, topic. Please consider this here. Now I will replace the slide I will find in any case. And in any case, I will upload also this material, this final manuscript. Of course, also the tutorial will be available in my site. This week I will organize everything. Anyway, let me stop now recording. Thank you for your attention. And we have 10 minutes, 5 minutes, 10 minutes to discuss the question and so on. But you will see that during the weekend, if you have time, you can download the material from my study. I will be able also to finish the YouTube channel. And of course, for the test or the exam exercise next week, I think should be a little bit more clear than at the beginning of the course. Yeah, because the examination is within 2 weeks, right? Within 2 weeks. Yeah. In any case, these days you have everything. Next week on Wednesday here or per Zoom directly. We will see, because today now I am just with a student. It makes sense that next week I can do from home. But if I am here, I will inform you, so you can come. Thank you for your attention. I am here nevertheless for questions.